Okay, we carry on today with Power Amplifiers, Chapter 7. We are going to distinguish between the different classes. As you can see there on my introductory page, Class A, Class B, Class AB, Push-Pull, Class C amplifiers. So by the end of this period, you should know the difference between those classes and so forth. But please open your textbooks and mark as indicated because we're not doing the complete chapter, the same as we didn't do the complete chapter of chapter 10. This is just an introduction of this specific theory that I want you to know. Okay, so if we turn to chapter 7 on page 323 and we read the introductory paragraph there just to see what it's all about. Power amplifiers are large signal amplifiers. This generally means that a much larger portion of the load line is used during signal operation than in a small signal amplifier. In this chapter, we will cover 4 classes of power amplifiers: Class A, Class B, Class AB, and Class C. These amplifier classifications are based on the percentage of the input cycle for which the amplifier operates in its linear region. Alright, but I will show you now how that's going to work. Each class has a unique circuit configuration because of the way it must be operated. But the emphasis is on power amplification. Power amplifiers are normally used as the final stage of a communications receiver or a transmitter to provide signal power to speakers to a transmitting antenna. Now the first one that we're going to discuss is the Class A power amplifier. You can mark the introductory paragraph there, where it says, when an amplifier is biased such that it always operates in the linear region where the output signal is an amplified replica of the input signal, it's a Class A amplifier. Does it sound familiar? Basically what we have discussed up to this point, as they say here in the introduction as well. The discussion of the amplifiers in the previous chapters applied to Class A operation. Power amplifiers are those amplifiers that have the objective of delivering power to a load. This means that the components must be considered in terms of their ability to dissipate heat. Okay, but if we go and look at figure 7.1 quickly, there's a block diagram of an amplifier, symbol for an amplifier, not a block diagram, symbol. Class A operation. And see my input signal and my amplified output signal, replica of the input, only that it is it's 180 degrees out of phase as we've seen with the, well, mostly of course with the common emitter amplifier, the one that you're also going to build in the lab. Alright, so linear operation. Linear operation, I know that my amplifier signal has to remain between cutoff and saturation. Because we've also seen when it is too close to cutoff, portion will be cut off. I have distortion, amplifier doesn't operate linear anymore. And of course the same happens to when the Q point is too close to saturation. Then I also have clipping, so then it's not operating linearly. Alright, so that is what we've discussed basically up to this stage. I also want you to mark here in your textbooks those paragraphs as I have marked them. In a small signal amplifier, the AC signal moves over a small percentage of the total AC load line. When the output signal is larger and it approaches the limits of the AC load line, the amplifier is a large signal type. Both large signal and small signal amplifiers are considered to be a Class A if they operate in the linear region at all times, as illustrated in the figure. Class A power amplifiers are large signal amplifiers with the objective of providing power rather than voltage to a load. As a rule of thumb, an amplifier may be considered to be a power amplifier if it's rated for more than 1 watt, and it is necessary to consider the problem of heat dissipation in components. As you've seen surely with the subject that you should have done before this one, in electrical engineering and in electronics 1, heat is always the problem. Get rid of the heat that is generated in these devices. So let's mark that section on heat dissipation as well, just below figure 7.1. Power transistors and other power devices must dissipate a large amount of internally generated heat. For BJT power transistors, the collector terminal is the critical junction. For this reason, the transistor's case is always connected to the collector terminal. The case of all power transistors is designed to provide a large contact area between it and the external heat sink. Heat from a transistor flows through the case to the heat sink and then dissipates it into the surrounding air. Heat sinks vary in size, number of fins, and type of material. Their size depends on the heat dissipation required on the maximum ambient temperature in which the transistor is to operate. In high power applications, a few 100 watts, a cooling fan may also be necessary. But I'm sure you've all seen heat sinks on the back of amplifiers, a piece of metal, as they said there, different metal, different alloys, with all these fins, so that the heat goes in there, and because of the air flowing through it, that it dissipates the heat so that the devices can work at higher power ratings. Alright, then the centered Q point, just to distinguish again, recall that the DC and AC load lines intersect at the Q point, and when the Q point is at the center of the AC load line, a maximum class A signal can be obtained. So just to remind you again about a class A amplifier. On the next page, page 325, power gain. We're not going to do any calculations in this chapter, so it's all just background theory. That's why I just want you to mark some of the sections here. But the power gain, a power amplifier delivers power to a load. The power gain of an amplifier is the ratio of the output power, that's the power delivered to the load, to the input power. In general, power gain is AP over is equal to PL over Pin, where AP is the power gain, PL is the signal power delivered to the load, and Pin is the signal power delivered to the amplifier. So just for interest's sake then the other thing I still want you to mark is on page 328, the efficiency. The efficiency of an amplifier is the ratio of the output signal power supplied to a load to the total power from the DC supply. And just below those formulas, the maximum efficiency of a capacitively coupled Class A amplifier cannot be higher than 0.25 or 25%. In practice, it's usually considered less, about 10%. But if you are asked what is the efficiency of a Class A amplifier, say that it is maximum 25%. In general, the low efficiency of a Class A amplifier limits their usefulness to small power amplifications that require usually less than 1 watt. Please underline those sentences. Alright, that concludes the Class A amplifier. Let's have a look at the Class B amplifier. Alright, we've seen for a Class A amplifier, as we've seen in the previous chapters as well, I have to bias it. First I bias it so that I can get the Q point in the middle of the load line so that my input signal has maximum swing between cutoff and saturation. Now let's have a look at this amplifier. Class B amplifier. If we go and have a look at figure 7.6, input signal, amplifier, but have a look at the output signal. Definitely not linear operation, is it? Definitely not linear. So what would happen for the output signal to look like that? Let's go back to our characteristic curve of the transistor again, of IC against VCE, where I got my Saturation points and cutoff points connected to the load line. I know for linear operation, I have to work between cutoff and saturation points. For class A, remember the Q point was determined by IBQ, VB, IBQ. That gave me my Q point for class A amplifier. Now what do you think happens with the class B amplifier? I can see, it seems to me, it's only the positive alternation of the input signal, isn't it? So, if I do not bias the amplifier at all, where's the Q point going to be? When IB is equal to 0. That is cutoff point, no? So, what can I see? That the class B amplifier is not biased at all, or they say it's biased at cutoff. So that's a B. So what happens? I know that the condition for amplification is that the base emitter junction should be forward biased and the base collector junction should be reverse biased. Not met at this stage. No. Let's go and have a look at the book. Introductory paragraph. When an amplifier is biased at cutoff so that it operates in the linear region for 180 degrees of the input cycle and is in cutoff for 180 degrees, it's a class B amplifier. Class AB amplifiers are biased to conduct for slightly more than 180 degrees. I will explain all these with the aid of sketches to you now. The primary advantage of a class B or a class AB amplifier over a class A amplifier is that either one is more efficient than a class A amplifier. Remember, class A amplifier has maximum efficiency of 25%. You can get more output power for a given amount of input power. A disadvantage, underline, of a class B or a class AB amplifier is that it is more difficult to implement the circuit in order to get linear reproduction of the input waveform. The term push-pull refers to a common type of class B or a class AB amplifier circuit in which two transistors are used on alternating half cycles to reproduce the input waveform at the output. But we will discuss it in full detail just now. Alright, so as we've seen in figure 7.6, the Q point is at cutoff. Class B amplifier is biased at cutoff point so that ICQ is equal to 0 and VCEQ is equal to VCE cutoff. Alright, so let's go and have a look at the next figure. There I can see. Can you see there's no biasing, there's no VBB, there's no voltage divider, nothing. No biasing is done on a class B amplifier. Only the signal that is applied, the input signal. So the input signal is applied, what happens? VBE must reach at 0.7 first, no? Then it conducts that portion, and when it goes below approximately 0.7 again, it switches off. So all these are not, go away, are not amplified. So you can see what the output signal looks like. Alright, so you can see no biasing. When there's no biasing, so the Q point is at cutoff, then it's a class B amplifier. You have to be able to draw this and the input and output waveforms with a simple explanation. Alright, as we've read in the introduction, it's a bit more difficult to get linear reproduction of the input waveform. So what can I do? Let's have it the next section there in the book. Class B push-pull operation. The bottom of page 330. It says there, Class B push-pull operation. As you can see, the circuit in figure 7.7 only conducts for the positive half of the cycle, even it's actually a bit less. To amplify the entire cycle, it is necessary to add a second class B amplifier that operates on the negative half of the cycle, because that's not amplified at this stage at all. The combination of the two class B amplifiers working together is called push-pull operation. One for the positive half, one for the negative half. Now there are two types. Make sure that you get the name correct. Some students give me the strangest names. Two common approaches. The first one, transformer coupling. Transformer coupling. Now if we go and look at that circuit, you can see the transformers. What type of transformers are used here? You use them in electronics 1 for full wave rectification. Center tap transformers. Can you see that? Characteristic of a center tap transformer on the secondary side. Two waves, 180 degrees out of phase. Same principle that's been used on the full wave rectification. Alright, here I've got my two NPN transistors, and Q1 is conducting for the positive alternation, Q2 is conducting for the negative alternation, and I have an amplified linear signal on the output. Linear. Why do I do this? It's not 100% linear, is it? It's still no biasing. So, but let's discuss the other type first. You have to be able to draw the sketch and do a simple description of the operation. There's the next one on page 331, complementary symmetry transistors. Complementary symmetry transistors. Using two emitter followers. You are familiar with the emitter follower already? Okay, so what is going to happen here? I can see here for the positive alternation of my signal, Q1, which is an NPN transistor, is going to conduct for the positive alternation. Negative alternation, I can see Q2, which is a PNP transistor, is going to conduct for the negative alternation. Alright, so the positive and negative alternations are amplified. But is it linear? Is it a linear amplifier already or not? Can you remember the transistors aren't switched on? So we need that 0.7 volts for both transistors before the base emitter junctions are forward biased and the conditions are met for linear amplification. Alright, so although the condition is much better, we have now a class B push-pull amplifier. It's not only the positive alternation, now it's the positive and the negative alternation. But I still have a problem. Let's have a look at the problem. This is what the output waveform looks like. So I'm not getting signal loss at saturation and cutoff, but I'm getting it in the middle because no biasing. I still need VBE for both transistors. You have to be able to draw this waveform, input and output waveform, with labeling. If you don't do the labeling, you also won't get all your marks. But here you can see positive alternation, as we've seen in the circuit. Q1 is conducting, Q2 is off. Negative alternation, Q1 is off, but now Q2 is conducting. But the problem is here. Q1 and Q2 are off because of those 0.7 volts, and that is called the crossover distortion. Crossing over from the one transistor, positive alternation, to the negative alternation. I have a dead spot there, crossover distortion. So actually my amplifier is still not 100% linear. How can I get rid of it? There's the solution. Now what is this amplifier now going to be called? First we started with the class B, and then the class B was only the positive alternation. Then we did the push-pull, positive and the negative alternation. Now what are we going to call this one? When we did biasing, what was that amplifier called? A class what? Class A, So I did the biasing, it was a class A. So what do you think? On page 332, biasing the push-pull amplifier for class AB operation. Class A was biasing now. So now it's a class AB amplifier, but a push-pull amplifier because both alternations, but now I'm also doing some biasing. So how is the biasing done? How is the biasing done? Remember in the introductory paragraph we said it's difficult to do this. Why is this difficult? See what I've done. I've done some biasing. I've got the voltage divider here again. But I'm also using two diodes. What was the problem? The 0.7 volts here. Nah. What is the volt drop over a diode that is forward biased? 0.7 volts. Nah. But what do we know? It's not exactly 0.7 volts. And that's where the difficulty comes in. I have to find a transistor and a diode which has approximately the same voltage drop over the forward biased p-n junction. That's where the difficulty comes in. So I'll have to go and measure some diodes and some p-n junctions of a transistor so that I can get them closely matched. As soon as I've got them closely matched, then that biasing problem is over. Then I don't have that dead spot of the 0.7 volts in both these cases. Alright, you have to be able to draw that circuit diagram. That's the solution for crossover distortion, and explain. Here it is in your textbooks on page 332. Biasing the push-pull amplifier for class AB operation. Mark that paragraph. To overcome crossover distortion, the biasing is adjusted to just overcome the VBE of the transistors. This results in a modified form of operation called class AB. In class AB operation, the push-pull stages are biased into slight conduction even when no input signal is present. We did the same with the class A amplifier. I also did the biasing without no input signal. Then I applied the input signal there. This can be done with a voltage divider and diode arrangement as shown in figure 711. When the diode characteristics of D1 and D2 are closely matched to the characteristics of the transistor's base emitter junctions, the current in the diodes and the current in the transistors are the same, and this is called current mirror. This current mirror produces the desired class AB operation and eliminates crossover distortion. Alright, so it's that paragraph for a class AB operation of a push-pull amplifier, and of course also figure 711 just below that paragraph that you have to know. Alright, so that's class B push-pull and class B push-pull amplifier for class AB operation. And then the only other thing I still want you to mark, of course, is the efficiency. On page 337, the maximum efficiency for a class B amplifier, a class AB, is slightly less, 79%. I can see the efficiency is much higher, although it's much more difficult to get 100% linear operation. Recall that the maximum efficiency for a class A amplifier is 25%. Alright, that concludes the class B amplifier. Let's do the last one, the class C amplifier. Mark that introductory paragraph again. Class C amplifier. Class C amplifiers are biased so that the conduction occurs for much less than 180 degrees. Class C amplifiers are more efficient than either class A or or a push-pull class B and class AB, which means that more output power can be obtained from class C operation. The output amplitude is nonlinear function of the input. So class C, underline this, so class C amplifiers are not used for linear amplification. Not used for linear amplification. They are generally used in radio frequency applications, including circuits such as oscillators that have a constant output amplitude and modulators where a high frequency signal is controlled by low frequency signal. Alright, so let's see what this amplifier looks like. There's a basic class C operation. Input signal. But see how it compares, how the output signal compares. You can see it's not even the positive alternation. It's much less than the positive alternation. So how do you think that is accomplished? How do you think that is accomplished? If we can revise quickly. The characteristic curve. What am I doing? That's VCE, of course. Saturation, cutoff, load line. Remember that was Q.4, Class A amplifier. That was the Q.4, Class B amplifier. So how am I going to get that output waveform? Look what happens here. Can you see I have biasing again? But negative VBB. Negative VBB. So what's going to happen? So class C, Q point is going to sit below 0 because I'm biasing it negatively. I'm biasing it negatively, as I can see here. So here you can see on the input and output waveform, what has to happen? This input signal has to overcome this negative voltage and the 0.7 volts, as you can see here. Only when that point is reached, you can see only that portion of the signal is amplified, and that is why output signal looks like that. Alright, so it's even negatively biased. Alright, so you have to be able to do that circuit and the input and output waveforms for Class C amplifier. So Class C amplifier, if we go back to the textbooks there, on page 341, as I've underlined there, a Class C amplifier is normally operated with a resonant circuit load, so the resistive load is used only for purpose of illustrating the concept. It is biased below cutoff with a negative VBB supply, as we've seen in figure 722. And then on page 343, because the tuned operation, remember that's where it's used, because the collector voltage output is not a replica of the input, the resistively loaded Class C amplifier alone is of no value in linear applications. Mentioned it a few times already. It is therefore necessary to use a Class C amplifier with a parallel resonant circuit, also called a tank, as shown in figure 724. Alright, so here in the circuit I can see there is my tank circuit, but again my negative biasing for the specific amplifier, so that's where it's used. I'm not going to ask you to explain the operation of the circuit, be able to recognize it and name it. Then lastly, the efficiency, of course, of a Class C amplifier at the bottom of page 345. Bottom of page 345, I can see when P out is much larger than PD averaged, the Class C efficiency closely approaches 1, which is 100%. Close to 100% because efficiency is compared with the input DC power, and I'm only amplifying a small portion of the input signal. That's why it's almost 100%. Right, but again, it cannot be used for linear operation. Cannot be used for linear operation. Alright, that is it. Just the sections that I've shown you. The difference between the amplifiers, their circuits, their waveforms, and then of course crossover distortion and how to get rid of it. So read through the sections discussed, and as I say here, you should be able to explain the basic concepts with the aid of sketches. Alright, that concludes chapter 7.